Welcome back. I ended right in the middle of a lecture on my elements, or my lecture on elements. And so we're going to pick up from that last slide where I talked about autotrophs and heterotrophs. And I want to move into a slide that, again, I've already mentioned that I'm going to come to this often about the importance of microbes. But here is also kind of a fun little trivia I was just discussing with my boss here about this. Star Trek was really good about talking about some of this stuff before we even knew what it was about. Things like symbioses. And back in the 60s, they had, McCoy talking about symbioses, presumably. They knew that these microorganisms in rocks were really important. These are slides, or these are images of three very important symbiotic interactions. You know what mitochondria are, right? They're the workhorse in our cells. They crank out all the energy, taking glucose, making ATP, and helping us live. If you look at that slide, you're looking at a bacterial fission. Mitochondria has DNA from bacteria. It's an endosymbiont. You could actually see the endoplasmic reticulum over there in the upper right especially. So we don't live without bacteria in our cells. They've lost the ability to live on their own, so they really need us for the house, if you will. I'll come back to that later. But we get all that energy from those bacteria. Where would we be without them? Chloroplasts, bacteria, DNA inside. They are also an endosymbiont. And plants have mitochondria as well, just to make sure we understand they could do both, or they do both, photosynthesis with those chloroplasts and respiration with those mitochondria. And then the last one there is the nitrogen-fixing root nodules. Not quite as intimate an association. The bacteria can live on their own, but those little arrows are pointing to nodules that are sort of reddish. I'll talk about this more later, but they're reddish almost for very similar reasons to why your blood is red. There's molecules in there that are taking up the oxygen and sequestering it and keeping it away from the bacteria that are mostly anaerobic, and then they could do their nitrogen fixation. And when you cut a nodule in half, you see it turns red instantly because the hemoglobin, not the kind you have, but a different one, binds up the oxygen when it shows up. Anyway, those bacteria can live on their own in soils. So kind of interesting, is it going towards true endosymbiosis, like a chloroplast, or are they going to remain sort of unique organisms? We'll see in about 50 million years or so. All right, where would we be without bacteria? Even more so, look at this slide. Now, I want you to memorize all those No, you do not need to memorize all those equations. The point here is a Winogradsky column allows you to set up a little mini ecosystem that includes anaerobic and aerobic conditions. And so at the top of this column, where they stuffed it, they put in mud, added water, probably from a mud flat. I think this one was made with sand. And then they just let it sit. And over time, just like a terrarium, it becomes its own little system. And anaerobic down at the bottom, and you have production of hydrogen sulfide. That's why when you stick your boot in mud, often it comes out stinky like sulfur. And sulfate is getting taken up by the bacteria actually diffusing into the area where the sulfate is being lost through metabolism and released as a gas. And so you have this sort of cycling going on by very unique bacteria, disulfibrio and some others, purple and green S bacteria, sulfur bacteria. And you can see the chemical reactions that they're doing. The bacteria are incredible. They're doing all sorts of stuff. And it behooves us as ecologists to think more about that, figure out what's going on there and how that might be utilized to help stabilize our environments, our habitats. Okay, and I suppose the other main point of this particular slide is the title. They are hugely important for energy transformations, both in anaerobic and aerobic settings. So next I want to talk about that endosymbiont that we call chloroplasts. And they're in algae, they're in ferns, they're in redwoods, they're in cherry trees. And they are using PAR, photosynthetically active radiation. That's a nice circular title. It is called that because it is what it does. Okay. But what is that area in the spectrum? Now, you probably know that or have an idea that gamma rays are kind of not good for you. It's because they're very high energy, very tight wavelengths. And when that hits your cell, it can nick your DNA, it could do all sorts of damage, cause mutagenesis and such. X-rays as well, but not as much. But you are always asked by the dentist if you could have another X-ray, because how many of you had in the last year? Probabilities are if you keep getting them, you may wind up having an issue. Probably not. Probably not, but it can happen. UV rays. How many times did I sit out in the sun? This weekend, several times. Again, taking my chances. All high energy, going from high to incredibly high. And then low energy, infrared, which is what you feel with heat, on up to microwaves, how we cook our food, and out to radio waves, how we transmit, well, in the old days, how we transmitted signals to each other and listened to our radios. In the middle here is the PAR from 400 to 700 nanometers, and that would be a good range for you to memorize. 400 nanometer wavelengths, you're venturing into ultraviolet where a bee can actually see better than you can. And then 700 nanometers, again, that's where you get heat from a stove or a fire or something like that. It's also the rainbow. And it's kind of interesting to me that the exact same range that plants are using to make energy, to capture energy from the sun, we also capture with our eye pigments as a rainbow. I don't know why. It seems to be the perfect radiation for quite a few things. Not too much to hurt, not so little to be useless for organisms. All right, and here are some organisms. These are algae that I'm going to put on my glasses here to make this a little more readable for me. On the right, you have the red algae. They tend to be in the deep waters. That's over here. And the reason they're red is because they don't absorb red light waves. So when you bring them up out of the deep water, they are red. They're reflecting the red. And oranges and things like that. And if you look in this figure, the carotenoids, those pigments that are picking up green and blue light, and that's the gray bar here, goes up 2 peaks right in here, starting down here. I don't know if you could see my laser there, but it's this gray one is very active at absorbing blue and green, and then it drops to nothing when you get to the yellow, orange, and red. That's why red algae is red. Why doesn't it absorb red? Because red light is too low energy to get through the deep waters of the ocean. These red algae live at the bottom, and red light doesn't make it down there. And so they have to rely on the short wavelength, high energy, blue and green pigment light to pick up energy from the sun. Now the green ones, these are up at the surface. They are getting bombarded by red and orange. They have the capacity for picking up green and blue, mostly blue. And these are the white bar and the black bar. But they also pick up the red pigments. And so why are they green? Because they reflect off the green and the yellow. It's not as high energy for them. They are picking up the red because a lot of times these things are way up at the top and there's no competition with anything else, and the low energy is probably just fine for what they need. Okay, So that's the spectra for light for plants. And now we move on to another sort of subtopic here. What I say is air. What is it? So what's air made out of? You're breathing it. So in order of which elements, what's mostly in air that you breathe? You might think CO2 because of global warming issues. You might think oxygen because we need oxygen to live. But you might also say nitrogen. You'd be right. Nitrogen gas, 70% of the air you're breathing is nitrogen gas. You breathe in, you can't do anything with it, you breathe it out. A root nodule with nitrogen-fixing bacteria is taking that nitrogen gas and making it into ammonium, for amino acid. And we rely on that feature. So we can't use the nitrogen from the air, but the bacteria can. We do use this oxygen. It has not always been at 21%, as you can imagine, prior to the evolution of things with chloroplasts or photosynthetic machinery. But now we have quite a bit of oxygen in the atmosphere. And then the last item that I want to point out to you is this carbon dioxide. Look how much, 0.039%. It doesn't take a lot of carbon dioxide to change that number. And that's why we are so kind of worried about this climate change thing, because just a little bit of CO2 is really doubling potentially the amount of CO2 in the atmosphere. It has been a lot higher in the past, but this was a different planet. I don't recommend us going back, but I'll explain that later. One of the nice things, and I talked about this already, about the oceans, is that there's a lot of, there's water. There's also calcium. That's going to come later. But you can see that CO2 is in equilibrium between the atmosphere and the ocean, or any body of water. And what's happening is the CO2, some of it dissolves into the water, and then it reacts with water to form carbonic acid, and eventually the bicarbonate ion pool. That interacts with calcium, and that makes calcium carbonate. The old days I talked about where the CO2 was super high in the atmosphere, the biggest reason for it isn't because plants arrive and make coal beds and oil and all that. That's important, but the majority of that high CO2 concentration in the atmosphere went to calcium carbonate through this reaction first of CO2 to dissolve carbon to carbonic acid, and then this molecule reacts with the calcium, and calcium carbonate precipitates out. Where did it go? To the ocean bottom, became limestone. That got metamorphosized to marble, right? There's a lot of these deposits worldwide, and most of that probably came from that early high CO2 concentration in our atmosphere. Okay, air versus water, a little bit more on this. CO2 is not limiting in either body, if you will, but oxygen, as you know, can be limited in water, usually not in air, and that forms our anaerobic conditions, and obviously a problem. But again, microorganisms are okay with that. Even fungi, there are some fungi that are very capable of living in anaerobic conditions, which is kind of an interesting feature. Now, why is CO2 so abundant in water? Think about that for a minute. Have you been paying attention on that last slide? That's why. CO2 is constantly going into the water, but it's getting diverted back into carbonic acid and then into the bicarbonate pool and limestone, right? So there will never be a shortage of CO2 for our water. You could constantly put more CO2 in there, and it will be always abundant in theory, and it is more abundant there than it is in our air. Sorry. Okay, other important nutrients. after HCO, hydrogen, carbon, and oxygen. These are ones that I want you to learn, and I'm serious this time. HCO, definitely, and then nitrogen, phosphorus, sulfur, potassium with a K. That's the Greek spelling of potassium. Calcium, magnesium, iron, and sodium. Those are all very important, and they will come up more or less during the semester at times. But you could also pick up a fertilizer box at the garden store, Miracle Grow. Look on the back. The big players are NPK, nitrogen, phosphorus, potassium, and then the micronutrients, which are the rest. Okay, so except HCO, those are not in there. And they all influence the abundance of life on the planet, are involved with energy transformations as well as nutrients and things like that. That picture on the right, HCO, when I was really getting into teaching this back in the early 2000s, I was like, wow, how cool that there's a company out there that is honing in on the three most important elements in this planet. Didn't hurt that they were from California, the actually epicenter of earthquakes, Hollister, California. And I thought that was just so cool that that company had honed in on HCO. And then one day in lecture, I kind of just for a kick, asked everybody, do you know why they used HCO? They're like, yeah, it has nothing to do with hydrogen and carbon and oxygen. That stands for Hollister Company. That's the name of the company, HCO, Hollister Company. And, oops, if you could go back to the back out of that slide, over there on the left is my little quip about when I learned. You imagine my surprise when I learned HCO had nothing to do with hydrogen, carbon, and oxygen, presumably, but was just short for Hollister Company, HCO. Okay, so professor as knucklehead, that's what that little side lesson is. Okay, here is something you've all seen, some version of this. This one happens to be color-coded by the type of element, alkaline, let's see, quickly grab my glasses. Yeah, alkali metal, transition metal, basic metal, etc. I don't want you to memorize that. I want you to memorize the rest of the chart, though. No, I don't. Don't want you to memorize this chart. I'm going to hone in on the ones I've already told you and show you where they are on this chart. And these are the ones you do need to know. Hydrogen, carbon, nitrogen, oxygen, over here on these last ones over here, right? Carbon, nitrogen, and oxygen over here. Silica, we haven't talked about, very important for diatoms in the ocean. We'll come back to that. Phosphorus, sulfur, and here's our hydrogen, our proton. That's the beast that is involved with all the acidity on the planet. Okay, another group, over here on the left, sodium, magnesium, potassium, and calcium. All right. You don't even need to know their atomic weight. You don't need to know the information that is also kind of embedded in this beautiful periodic chart of the elements. But you need to know that if you see something that says Na, that means sodium. If you see something that says N, that means nitrogen. All right. If you see something that says K, right, potassium. You have to remember that refers to a P word, potassium. So I want you to learn those, and you will be seeing them highlighted at various times throughout the lecture. Here's another group that are very important. Chromium, manganese, as opposed to magnesium. Again, trace elements that are important for plants. And then iron, cobalt, nickel, copper, zinc. And then, aluminum. Very important in our soils, basically. Probably toxic a little bit. All of these can be toxic at high concentrations, so the trick is to get them at the micro level. The last one here is chlorine over on the right. That's very important for sodium chloride, but also for ridding yourself of viruses. No, that was a joke. I'll stop. Let's see, there was another thought there. I think I'll just stop and acknowledge that it must not have been important enough because I don't remember what it was. Okay, so that's the periodic chart, and that gives you a sense of which ones I want you to hone in on. Oh, I know what it was. There's a lot of other elements here. When you get down to here, these are the radioactive ones that show up for a flash after they bombard atoms with other atoms. And fun names like nobelium and berkelium. I wonder where that was found. Lawrencium at the Lawrence Hall of in Berkeley. So anyway, you don't need to know those, obviously. They're also pretty bad, pretty radioactive and carcinogenic, mutagenic. All right. So in summary, for the living things portion of this lecture, all living things function within the limits set by physical laws. I didn't dig into that a whole lot, but that's in the chapters, and you want to look at that. We all depend on the physical world for our energy and our nutrients and water. And we are all altering the physical world. You know this just through conservation issues, but I want you to think of it in terms of nutrient cycling, where we are taking sugar, cranking out CO2 and water, doing other things through our waste products. You can't possibly live on the planet without altering it. And the more we understand that, I think the better off we'll be. So that is the end of this segment. I have another lecture to go that is tied to this, that starts looking at not just how organisms are adapted to the environment, but how they're adapted to variations, a gradient of salt. Same organism, how does it deal with high concentration to low concentration? And you can imagine it gets kind of reductionist at that point. You start talking about molecules in the body of the organism. So that's it for this segment, and we'll see you next time for variations in the environment and the adaptations we have for those.